This comes in handy when we have to estimate the probability of at least one event. Remember the Browns with their daughter, or perhaps two? Since having at least one daughter is the same as not having all sons, then instead of calculating the disjunction, first child is a girl, or second child is a girl, we could have calculated the complement of a conjunction, 1 minus the chance of having all boys, which is 0.25, namely 0.75. In the case of two events, it doesn't make much difference which formula we use. But when we have to calculate the probability of at least one A in a large set, the disjunction rule requires the tedium of adding and subtracting a lot of combinations. It's easier to calculate it as the probability of not all not A, which is simply 1 minus a big product. I basically checked that. I'm just reading it for you guys. I'm hoping, it looks like we're going to get it. This is going to stop soon. Suppose, for example, that every year there's a 10% chance of a war breaking out. What are the chances of at least one war breaking out over a decade? Let's assume that wars are independent, not contagious, which seems to be true. Instead of adding up the chance that a war will break out in year 1 plus the chance that it will break out in year 2 minus the chance that one will break out in both year 1 and year 2 and so on for all combinations, we can simply calculate the chance that no war will break out over all of the years and subtract it from 1. That is simply the chance that war will not break out in a given year, 0.9, multiplied by itself for each of the other years. 0.9 times 0.9 times 0.9, or 0.9 to the 10th, which equals 0.35, which when subtracted from 1 yields 0.65. Sure. Finally, we get to a conditional probability. I think that, if you ask me questions to test my understanding of this, no, I can't make any promises. Because I don't know whether it's just I'm just not connecting with these words. And not because it's these words, but just because my brain doesn't connect well with math words. But my brain, I think, is good at sort of math or something. It can't be because it got hard in school with the words. But anyway, moving on. Finally, we get to a conditional probability. The probability of A given B, written as prob bar B. A conditional probability is conceptually simple. It's just the probability of the then in an if-then. It's also arithmetically simple. Oh, thank God. Okay, thank God. I'll let someone else deal with the so-its. In a previous video, we named the disjunctive its as the so-its, coming from the word soit, S-O-I-T, in French, which means either, and then soaks it for the exclusive. Okay, so back to our normal its of just given a certain thing, there's a then. It's also arithmetically simple. It's just the probability of A and B divided by the probability of B. Nonetheless, it's the source of endless confusions, blunders, and paradoxes in reasoning about probability, starting with a hapless fellow in the XKCD cartoon on the following page. Crack! Boom! Whoa, we should get inside.
That's okay. Lightning only kills about 45 Americans a year, so the chances of dying are only 1 in 7 million. Let's go on.
The annual death rate among people who know that statistic is 1 in 6. His error lies in confusing the simple probability or base rate of lightning deaths, prob struck by lightning, with the conditional probability of a lightning death given that one is outside during an electrical storm. Probability struck by lightning bar outside in storm. Though the arithmetic of a conditional probability is simple, it's unintuitive until we make it concrete. It's unintuitive, meaning sort of our natural its don't, or our natural its and the sum they currently make don't really align with it. Now, we might have its that very much align with this concept, but there's maybe interference from other its that are not aligned with it. That's what, by the way, unintuitive means. So back to page 134. Though the arithmetic of a conditional probability is simple, it's 135 unintuitive until we make it concrete and visualizable, as always. Look at the Venn diagrams on the page after the next one, where the size of a region on the page corresponds to the number of outcomes. The rectangle with an area of 1 embraces all the possibilities. A circle encloses all the A's, and the top left figure shows that the probability of A corresponds to its area, dark, as a proportion of the whole rectangle, pale. Sure. As a proportion of the whole rectangle, pale. Another way of saying the number of occurrences divided by the number of opportunities. The top right figure shows the probability of A or B, which is the total dark area, namely the area of A plus the area of B without double counting the wedge in the middle they share. That is the probability of A and B. That wedge, probability A and B, is shown in the lower left diagram. The bottom right diagram explains the deal with conditional probabilities. It indicates that we should ignore the vast space of everything that can possibly happen, bleached into white, and focus our attention only on the incidents in which B happens, the shaded circle. 136. Now we scrutinize how many of those incidents are ones in which A also happens, the size of the A and B wedge as a proportion of the size of the B circle. Of all the interludes in which people walk in an electrical storm, B, what proportion of them result in a lightning strike? A and B. That's why we calculate the conditional prob A bar B by dividing the conjunction, prob A and B, into the base rate, prob B. The bottom right image is not different from the bottom left one. The shaded areas are the same. Is that normal? It's not just the words. All right, hold on. Let me put this gum somewhere. All right.